Flutter has reached a massive adoption scale in 2026, driving nearly 30% of new iOS applications launched this year. Development teams often run these applications through standard security scanners and receive a report showing 0 vulnerabilities. This creates a dangerous illusion of security. Ahead-of-time compilation translates readable Dart source code into a highly optimized native binary. This optimization strips away readable logic and data flows. When a traditional security tool scans this block, it cannot reconstruct the program's structure, reporting 0 vulnerabilities simply because the code is unreadable. By prioritizing cross-platform performance, the framework destroys the context required for standard security audits, creating a significant observability blind spot. Traditional static analysis relies on finding abstract syntax trees, the structural maps of how code is organized. Because AOT compilation eliminates these structures, scanning a source code repository only provides a partial view of the threat model. Modern security for cross-platform apps requires a binary-first testing methodology. This approach focuses on the final compiled APK, or IPA, as it behaves at runtime, monitoring live network calls and data flows rather than the static source. Verifying a developer's original intent is useless if the audit ignores the actual compiled artifact that attackers will interact with. We begin the threat model at the first layer, vulnerabilities introduced during the developer's implementation. Many developers believe AOT compilation acts as a shield that prevents reverse engineering. In reality, any attacker can use basic extraction tools like APK tool to decompile the application package. Once extracted, standard terminal commands are often enough to scrape hard-coded API keys and backend secrets directly from the application files. The risk is compounded when sensitive session data is routed to unencrypted local storage formats, like shared preferences or standard Hive databases. Relying on compilation for obfuscation while using plaintext storage effectively packages and delivers sensitive user data to anyone with basic forensic tools. Hardware-backed encryption is the baseline requirement for all client-side storage. This involves routing data through the Flutter Secure Storage package, which leverages the native Android key store and iOS keychain. This bypasses standard application memory, locking tokens into a secure, isolated hardware container. Code obfuscation flags should be used to rename symbols and slow down attackers, though they do not provide a complete solution. They offer no protection against hooking, a technique where attackers use tools like Frida to tamper with the application while it is running on a rooted or jailbroken device. To counter this, applications must use Runtime Application Self-Protection, or RASP, to monitor the environment for debuggers and compromised device integrity. Effective security requires active runtime countermeasures to defend against attackers operating in compromised environments. The second layer of the threat model involves vulnerabilities found within the Flutter framework itself. This is exemplified by CVE 2026-27704, a path traversal flaw discovered in the Dart and Flutter package managers. Malicious packages were able to use symlinks to escape the restricted cache directory and write arbitrary files to the user's system. Deeper in the architecture, flaws like the libpng vulnerability sit embedded within the Flutter engine block below the application layer. Developers cannot patch this directly and must wait for the framework provider to release a secure engine update. These framework risks also manifest in the RustDesk remote desktop client, which suffered from a critical cross-site request forgery flaw. The client's URI scheme handler lacked privilege checks, allowing an external link to silently set a permanent account password without user interaction. Even with secure application code, framework-level CVEs can create unpatchable windows of exposure that bypass existing security controls. At the final threat layer, advanced actors are weaponizing Flutter's architecture to engineer highly evasive malware. Operation FlutterBridge demonstrated this through the deployment of a macOS backdoor called FlutterShell. To avoid suspicion, FlutterShell is disguised as functional desktop software, like this PDF viewer named PDF Brain. The interface looks professional and provides standard functionality. This legitimate facade, combined with the opaque nature of the compiled binary, allowed the malware to successfully pass Apple's official macOS notarization checks. The framework's ability to abstract the native layer provides a highly effective mask for infiltrating secure operating systems. To understand how FlutterShell evades modern detection, we have to look at its internal architecture. The actual malicious logic is not stored in the binary installed on the victim's system. Instead, the malware utilizes a hidden WebView component connecting to an external server. A message channel called Flutter Invoke bridges this remote web content and the local system. JSON-formatted commands cross this bridge, translating directly into native macOS terminal execution. Because the payload is decoupled from the application, attackers can alter the malware's behavior in real time, making static sandbox analysis ineffective. The primary goal of the FlutterShell campaign is silent browser hijacking and adware routing. The malware targets the Google Chrome Secure Preferences file, shown here. It overwrites the default search provider block with a domain controlled by the attacker. This forces all user web searches through intermediary sites that generate revenue for the threat actors. To remain persistent, the malware abuses the Sparkle software update framework, a legitimate tool used by many macOS applications. FlutterShell interrupts the standard update protocol to bypass the required user consent prompts, forcibly killing and relaunching processes to install updates silently. By weaponizing trusted software lifecycle mechanisms, attackers are able to establish deep and silent control over the system. In 2026, defense requires an active lockdown of the runtime environment. We must accept that source code analyses is no longer a sufficient proxy for application security. Modern threats make binary-first testing a necessity for accurately modeling live attacks and observing actual runtime execution. Hardware-backed secure storage and active RASP implementation are the standard requirements for detecting and stopping live tampering. As frameworks continue to abstract the native layer, security protocols must aggressively monitor the final execution environment to defend against the next generation of exploits.